Good afternoon. My name is Mrs. Tasnia. Today for the Machine Learning Driven Data Analysis course, I'll be presenting on one of the most robust and popular algorithms in the field, support vector machines or SVM. Imagine we have a dataset with two classes, red dots and blue dots. Our goal is to separate them. As you can see on the screen, I can draw line 1, line 2 and line 3. All of them separate the data perfectly. But here's the dilemma. Which line is the best? Line 1 is dangerously close to the blue class and line 3 is hugging the red class. If a new data point comes in, those lines might make a mistake. We need a way to define which line is mathematically safest. SVM solves this by looking for the widest street possible. We don't just want a thin line, we want a wide safety buffer between the classes. This buffer is called the margin. Think of the hyperplane as the yellow line in the middle of the road. The wider the road, the more confident we are that we won't crash, or in machine learning terms, the less likely we are to misclassify new unseen data. To understand how SVM works, we need to know three key terminologies. First, hyperplane. This is the decision boundary itself. In 2D, it's a line, and in 3D, it's a plane. Then we have margin. This is the distance between the central line and those support vectors. Our goal is always to maximize this distance. And for support vectors, they are the most important data points. They are the ones closest to the boundary, the pillars holding up our street. Interestingly, SVM only cares about these specific points. The rest of the data doesn't actually change the line. Now let's look at why these margins matter. It comes down to generalization. A small margin means that the street is narrow. If we see the image on the left side, we can see that the line is overfitting. It fits the training data completely, but a tiny variation in the new data could cause an error. And similarly, if we look at the image on the right side, we can see that the street is wider, which makes the model more robust. It ignores the noise and captures the general trend, making it more safer for real-world predictions. What will happen if our data is not linear? It cannot be separated using a linear line, a simple line. Let's look at the image on the left side. Here we can see that these two classes cannot be separated using a simple line. So what should we do? This is where SVM uses the kernel trick. So if we imagine that these dots are on a flat sheet of paper, the kernel trick will essentially lift the data into a 3D space. Once the data is floating in 3D, we can easily slide a flat sheet or a hyperplane between the two groups. This solves the complex nonlinear problem by projecting it into a higher dimension. Now let's look at some common kernel types. Depending on the shape of our data, we use different mathematical kernels. First, we have the linear kernel, which is used for the simple straight line problems. Then polynomial kernels that creates carved boundaries. Then we have the RBF, which means radial basis function. It is the default powerhouse. It is responsible for mapping data into infinite dimensions that helps the SVM to solve very complex boundaries. Now, let's look at the learning process of the SVM algorithm. First, the SVM will map the data into the space. Then, it will identify all possible lines that could separate the classes. In the next step, it will calculate the distance from those lines to the nearest support vectors. Finally, it picks the single hyperplane that provides the maximum margin. SVM is not just theoretical, it powers many technologies that we use in our day-to-day life. First of all, it's used for face detection. It decides if a part of an image is a face or a background. Then for handwriting recognition, and then for bioinformatics. Bioinformatics, it's used for classifying genes and proteins. Now let's look at the key takeaways about SVM. First of all, maximum margin means maximum safety. A wider boundary means there is a better chance of better prediction. Then edge cases matters. The model relies entirely on the support vectors. The rest of the data is actually irrelevant to the boundary. Then we have that kernels are powerful. Kernels actually allows the model to solve the complex nonlinear problems efficiently. These are the references that was used to build this presentation. Thank you.